After studying this module, you shall be able to know about the concept of uncompensated heat, learn about the thermodynamic potentials, derive relation between the chemical potential and thermodynamic potentials. Now let us first learn about the uncompensated heat. A non-equilibrium or spontaneous process described by equation of inequality as ds is greater than del q by t, which is based on the direction of spontaneous process. Clausius suggested different form of second law of thermodynamics based on equality, that is ds minus del q by t is equals to del q prime by t, where del q prime is uncompensated heat. It is not the actual heat absorbed or evolved by the system, but the heat that could have been absorbed in a reversible process in addition to non-equilibrium quantity del q in order to maintain equality. Rewriting the above equation, ds is equals to del q by t plus del q prime by t. For reversible process, del q prime is equals to 0, while for irreversible process, del q prime is greater than 0. Thus, del q prime is always positive and is produced in the system as a result of non-equilibrium process resulting in an irreversible change. Now we'll see the physical significance of uncompensated heat. Let the total entropy change of the system is the sum of two components, that is ds external, which is due to the absorption of heat reversibly from outside, and ds internal, which is due to the irreversible change occurring in the interior of the system. This means ds total is equals to ds internal plus ds external. Comparing equation 2 and 3, we have ds external is equals to del q by t and ds internal is equals to del q prime by t. Rearranging the above equation gives del q prime is equals to tds internal. Thus, from this equation, we can say that the uncompensated heat is related to the production of entropy as a result of some irreversible processes occurring within the system. Such processes can be mixing of gases, diffusion of solute from higher to lower concentration. The randomness in the system increases as a result of increase in the disorder in the state of system. Thermodynamic potential. At equilibrium, the extensive parameters U, S, V and Ni are function of state, and linear combination of these parameters are also state functions. Helmholtz, Gibbs and others have considered such combinations and have found that these are often more useful than the internal energy for describing systems under ordinary experimental conditions. Such combinations are called thermodynamic potentials. They are extensive quantities and must not be confused with the ordinary potentials, which are derivatives of thermodynamic potentials and are intensive quantities. Some of these thermodynamic potentials are: first, Helmholtz free energy. The Helmholtz free energy is given by the expression F is equals to U minus Ts. At constant temperature and volume conditions, we can write the differential form as dF is equals to du minus Tds. From the first law of thermodynamics, du is equals to Tds minus dW. Substituting this equation in the previous one, we get dF is equals to Tds minus dW minus Tds. and therefore we get dF is equals to minus dW at constant temperature and volume. Therefore, total reversible work performed by the system is equal to decrease in Helmholtz energy at constant temperature and volume. Now, differentiating equation 7 without any restrictions, we get dF as du minus TdS minus SdT. Using expression for du as TdS minus PdV plus summation of mu I dNi, we get the expression for dF as minus PdV minus SdT plus summation mu I into dNi from I is equals to 1 to k. This equation gives new definition of chemical potential. Therefore, we can write mu I as dF by dNi at constant volume, temperature and number of moles of all other components. Gibbs free energy, where Gibbs free energy is given by the expression G is equals to U minus Ts plus PV. Differentiating the above equation while keeping temperature and pressure constant, we get dG is equals to du minus TdS plus PdV. From the first law of thermodynamics, we have a relation du is equals to TdS minus dW. Substituting the above equation in equation 17, we have dG is equals to TdS minus dW minus TdS plus PdV. Therefore, we have the final expression as dG is equals to minus dW plus PdV. This equation shows the decrease in G is equals to the total work minus the work of compression, which Gibbs called the useful work, and dW minus PdV is equals to dW prime. It is that part of work which is contributed by chemical reactions or by the transport of electricity. In the study of condensed systems such as solutions, living tissues or solid material, PdV is usually small and generally does not contribute significantly to the total work, so that the choice of G as the characteristic potential is common practice. Now, differentiating equation 16 without any restriction gives dG as du minus TdS minus SdT plus PdV plus VdP. Since du is equals to TdS minus PdV plus summation mu I dNi, substituting this equation in equation 20, we get dG is equals to minus SdT plus VdP plus summation mu I dNi. This expression defines the chemical potential in its most familiar form, that is mu I is equals to dG by dNi at the constant temperature, pressure and number of moles of all other components. Enthalpy. Another common thermodynamic potential is enthalpy. It is defined as H is equals to U plus PV. For the closed system, dNi is equals to 0. Now, differentiating this equation, keeping the pressure constant, we have dH is equals to du plus PdV. If dNi is equals to 0, du plus PdV is equals to dQ at constant pressure, and hence dH at constant pressure is equals to dQ at constant pressure. Now, differentiating equation 24 without any restriction, we have dH is equals to du plus PdV plus VdP. Substituting the expression of du, we have dH is equals to Vdp plus Tds plus summation mu I dni. Therefore, mu I is equals to dH by dni at constant entropy, pressure and number of moles of all other components. Substituting equation H is equals to U plus PV into equation G is equals to U minus Ts plus PV, we find that the free energy is related to the enthalpy by the expression G is equals to H minus Ts. Now we'll see entropy. In natural or spontaneous processes, energy is conserved while entropy is not conserved. In such processes, entropy of the reaction increases. Entropy of the system is extensive property. The total entropy is the sum of total entropies of each individual part of system consisting of several parts, that is, if system is divided into R different part, then the total entropy is ds is equals to ds1 internal plus ds2 internal plus ds3 internal and so on up to dsr internal. Generally, where ds internal k is the entropy production of the kth part and dsk internal is greater than 0 for every k part. This states that in irreversible processes, the entropy production is positive in every part, and this statement is stronger than the classical statement of second law that the entropy of an isolated system can only increases or remain unchanged. Now let us summarize. The total entropy of the system is the sum of two components, ds external and ds internal, which are the entropy changes due to the change in heat in exterior and interior of system respectively. The relation between change in entropy and uncompensated heat is given by ds internal is equals to del q prime by T, where del q prime stands for the uncompensated heat, which is related as the production of entropy within the system because of some irreversible process occurring within the system. The thermodynamic potentials are mu I is equals to dF by dNi at constant Vt and Nk, which is the chemical potential in terms of Helmholtz free energy. Mu I is equals to dG by dNi at constant pressure, temperature and Nk, which is the chemical potential in terms of change in Gibbs free energy. Mu I is equals to dH by dNi at constant entropy, pressure and Nk, which is the chemical potential in terms of change in enthalpy. The entropy produced in every irreversible process is positive for every part of the system, that is, ds internal k is greater than 0 for every kth part of the system.